Okay, it's time for a few examples with current division. As with voltage division, we're going to do 4 examples here. I'm going to start out with one that's very straightforward. So example A, you can see that it's pretty much a textbook classic example of current division. We have 8 amps flowing in. We don't know how much I1 is. We don't know how much I2 is, but we can easily find I1. So I1 is going to be equal to the total amount of current. The S stands for source there. It could just as easily say I sub tot. And then that's going to be multiplied by the other resistor divided by the sum of the 2 resistors. So in this case, I sub S is 8 amps. This will be multiplied by the ratio. If I want I1, then this should be 6 amps or 6 ohms in the numerator, and then 2 ohms plus 6 ohms in the denominator, and therefore I1 is 2 amps. So, is 6 amps. And then I2 is IS times the other resistor R1 divided by R1 plus R2, which is 8 amps times R1 is 2 ohms, and this will be divided by 2 ohms plus 6 ohms, and therefore I2 is equal to 2 amps. 2 quick reality checks. Do the 2 currents add up to 8 amps? Yes, they do. And does the larger resistor get less current? The 6 ohm resistor is the larger one, and it gets less current. So yes, it is a good reality check. Both of those do in fact work out to be correct. So we're feeling good about those answers. Let's tackle a slightly more difficult problem. Here you can see that it seems that this problem would be more difficult. In reality, it's not that much worse. Let me just redraw the circuit first of all by combining the 5 ohm and the 2 ohms. So I'll redraw it. I don't know that I strictly absolutely have to, but I want to get into the good habit of redrawing the circuit frequently. So you can see here I have combine those 2 resistors into a 7 ohm resistor. This is labeled as I2 in the original circuit. This is labeled as I1. This is 3 ohms. This is 5 ohms. And this is 10 amps. Now here's the most interesting part about this problem is that the 5 ohm resistor makes no difference whatsoever. We know that from the current source, we know that there must be 10 amps flowing here. We know that there must be 10 amps flowing here. We know that I1 is flowing down here. And we know that I2 is flowing out here. This is the classic example of a place where we have 2 resistors in parallel. We know the total amount of current. It's 10 amps. We don't know how it's being divided. It's time for current division. So we can say that I1 is going to be 10 amps multiplied by the resistance of the other branch, 7 ohms, divided by the sum of the 2 resistances, 3 ohms plus 7 ohms. This works out to be 7 amps. And then I2 is 10 amps times the other branch's resistance, that's 3 ohms, divided by 3 ohms plus 7 ohms, and that works out to be 3 amps. Do the two currents add up to 10 amps? Yes, they do. Does the larger resistance, 7 ohms, I2, does it get the smaller current? Yes, it does. So I'm feeling pretty good about the reality check on those two answers. And notice that looked like it was going to be harder than it was. And the reason why it isn't harder is because this current source, the 10 amp current source, it just plows right past that 5 ohm resistor. And yes, the voltage is affected, but the current is not. The current going into that top node is still 10 amps. And that 10 amp current is being divided by current division. Okay, let's calculate the current I sub X in this circuit. Okay, I sub X is kind of in the middle of a pretty big conglomeration of resistors. The very first thing that I'm going to do is I'm going to redraw the circuit by combining these 2 resistors in parallel. I know that because they're equal resistors, I don't even have to do the equation. The equivalent impedance will be half of the original impedance. That'll be 4 ohms. So let me go ahead and redraw the circuit. So I have 8 ohms here. This will be 8 ohms. And this will be 4 ohms. And then this one will be 4 ohms. and this current is 12 amps. Now, just as in the third example or the fourth example on voltage division, I can't label I sub x on this new figure. I sub x is part of this resistor right here. It's part of the current flowing through that resistor, but it's not the whole thing. So I can't label I sub x anywhere on the revised circuit. But I can label some other things. I know, for example, that this is 12 amps. And let me just go ahead and label this as I1. You know, just because it wasn't labeled on the original circuit diagram doesn't mean that you can't label it. I'm going to label this as I2. Well, notice that I1 still exists. I1 is right here, and I2 still exists. I2 is right here. As a matter of fact, I2 is also right here. Okay, I'm going to go ahead and combine the two 4 ohm resistors that are in series. So let's redraw the circuit one more time. So I have 12 amps, and this is 8 ohms. And then those two 4 ohm resistors in series add up to 8 ohms. So you get 8 ohms as well. This is I2, and this is I1. And lo and behold, we've got a parallel pair of resistors with a known amount of current flowing into the combination. So this is 12 amps flowing in, and an unknown amount of current flowing through each of them. This happens to be the special case. I chose it that way so that the two resistors are equivalent. Therefore, I know that I1 equals I2 equals 1/2 of 12 amps, which is 6 amps. So I now know that I2 is 6 amps. Guess what? I2, all the way back up here, this is 6 amps. So I know now that 6 amps is flowing in this node. Part of it is going to flow down. This is labeled as I sub x. Part of it is going to flow out this way. It's not labeled, but I don't really care because what I was asked to find is I sub x. So I know that 8 ohms and 8 ohms, that's 2 equal branches. So that 6 ohm source, or that 6 amp current source is going to be split in half. I sub x equals, I'll go ahead and label this one as I sub y, just so that it's not confusing. So you have I sub x equals I sub y equals 6 amps over 2, which is equal to 3 amps. So we had to solve current division once to find I2, and then we had to solve current division a second time to split I2 into IX and IY. That's a pretty challenging example. We're gonna see examples like that again next time. So if that one is one that you're struggling with, we're gonna see more examples like that. Okay, and then we're going to calculate the current I sub A. It seems like this circuit is a little bit easier than the previous one, but here's the problem. This is a voltage source. Up until now, everything that we've been doing has been a current source, so we have to work with a voltage source now. That means that I need to get this all down to just one resistor so that I can calculate this current right here. Let me just, I'll call that I sub 10 for the 10 ohm resistor that it's going to pass through. Let me go ahead and combine the 8 and the 2 ohm resistors here. That's going to give me 10 ohms. And then you can see that once I combine those in series, that 10 ohms is going to be in parallel with the 20 ohms. So if I calculate what is R equivalent, it's 10 times 20 over 10 plus 20. That's 200 over 30. That works out to be 6.667 ohms. Okay, so I know that I can redraw the circuit and it'll look like this. I have a voltage source. That 10 ohm resistor remains unchanged. And I've now, in one step, combined the 8 and the 2 in series. Then I combine the 10 and the 20 in parallel, and I end up with 6.667 ohms. And then the 10 ohms remains unchanged. This is I10, as I labeled it in the original figure. This is 12 volts. By the way, that I10, that's now down to the same current that's flowing around the entire circuit. I can add those two resistors together. I have 10 ohms plus 10 ohms plus 6.667, and that's going to give me the total amount of current that's flowing. So R equivalent now is equal to 10 plus 6.667, and therefore R equivalent is 16.667 ohms. I can redraw the circuit one last time with just a single resistor, 16.667 ohms, 12 volts. And then I can calculate I10. I10 is equal to 12 volts divided by 16.667 ohms, which is equal to 0.72 amps. So I now know that this I10 up here is equal to 0.72 amps. That means that this is 0.72 amps. And I know that I have I sub A is the current that I'm looking for. That's this current right here. And so what I can do is I can write one last current division. I sub A is going to be the total current, 0.72 amps, multiplied by the ratio, where I want the numerator to be the other resistance. The other branch's resistance is the 20 ohms, and the denominator is going to be the 10 ohms. So it's going to be the 10 ohm equivalent of 2 plus 8. So this is going to be 10 ohms plus 20 ohms, and 0.72 times 20 divided by 30 is equal to 0.48 amps. So a bit more work on that one. And what we saw here in the last couple of examples is that we had to apply current division 2 different times. One to find a current earlier in the circuit, and then a second time to find the current that we were actually looking for.